The International Space Station took over 13 years to build, more than 40 missions, 5 different space agencies, and over $100 billion, all to assemble a structure with roughly 1,005 cubic meters of pressurized volume, which sounds impressive until you realize that a single SpaceX Starship upper stage has around 1,000 cubic meters of internal payload volume. If that space were converted into a habitat, one rocket could rival what took a decade of orbital construction to assemble, one launch. Enough volume to potentially match the biggest structure humanity has ever put in orbit. That comparison sounds almost too good to be true. And honestly, there are massive caveats we need to talk about. But the core idea of turning a Starship into a space station is not science fiction. NASA has formally signed an agreement with SpaceX to explore commercial low Earth orbit architectures that include Starship as a potential orbital destination, and there is a direct historical precedent for converting a giant rocket stage into a livable space station. NASA already did it once, back in 1973. So let's break down how this could actually work, what is standing in the way, and why the race to replace the ISS is way more interesting than you probably realize. To understand why the Starship station concept matters, you first need to understand the fundamental problem with how we have been building space stations for the last 50 years. Most major space stations since the 1970s have relied heavily on modular construction. You launch small pieces on separate rockets, then bolt them together in orbit using robot arms and astronauts in spacesuits. The International Space Station is the ultimate example of this approach. Its modules were launched inside the Space Shuttle cargo bay and on Russian Proton rockets, and each piece was limited by how much you could squeeze inside those vehicles. The widest International Space Station modules are about 4.6 meters across. That is roughly the width of a single-lane highway. The result is a station that works, but feels like a collection of cramped tunnels connected by hatches. Astronauts have described it as living inside a submarine. The construction process itself was a nightmare of logistics, with assembly flights stretching from 1998 all the way to 2011. Now, the International Space Station is scheduled for retirement around 2030. After more than 25 years of continuous human occupation, the oldest modules are showing their age, with documented cracks in the Russian Zvezda module, persistent air leaks, and aging hardware that NASA has flagged as the station's top safety risk. NASA needs a replacement, and they really do not want to spend another decade bolting small tubes together in space. Which brings us to a lesson from history that most people have completely forgotten about. In 1973, NASA launched Skylab, America's first space station, and the way they built it was brilliant. The Apollo program had ended early, which left NASA with unused Saturn V rockets. These were the same massive vehicles that sent astronauts to the moon. Rather than let them sit in a warehouse, NASA engineers looked at the Saturn V third stage, a cylinder called the S4B that was 6.6 meters wide and nearly 18 meters long, and asked a simple question: what if we just turned the rocket itself into the station? The original plan was even wilder. Engineers initially proposed a wet workshop concept, where the stage would launch full of fuel, burn that fuel to reach orbit, and then astronauts would go inside the empty tanks and convert them into living space. Imagine floating into a recently emptied rocket fuel tank with some tools and wall panels, trying to build an apartment in zero gravity. It sounds insane. Fortunately, when extra Saturn V rockets became available after the final planned Apollo lunar missions were canceled, NASA switched to the much smarter, dry workshop approach. They outfitted the empty S4B on the ground with floors, sleeping quarters, a shower, experiment stations, and a full life support system, then launched the whole thing in one shot. Skylab had about 360 cubic meters of pressurized volume. That single launch put more usable living space in orbit than any single module on the International Space Station, including Japan's Kaibo Laboratory, which at 150 cubic meters is the largest module on the International Space Station and still less than half of Skylab. The astronauts inside had room to do somersaults, play with physics experiments, and move around without bumping into each other constantly. 3 crews visited Skylab for stays of 28, 56, and 84 days before the station was eventually abandoned and burned up in the atmosphere in 1979. And here's where it gets really exciting, because the parallel between Skylab and Starship is almost eerily direct. NASA took a giant rocket built for deep space missions, gutted the insides, and turned it into the most spacious orbital habitat ever flown. SpaceX has built an even more giant rocket intended for Mars, and its upper stage has roughly 3 times the pressurizable volume that Skylab offered. The Starship upper stage is a stainless steel cylinder 9 meters in diameter and about 50 meters tall. Current SpaceX documentation describes a payload section roughly 8 meters wide and around 17 meters tall, with the total payload volume listed at up to 1,100 cubic meters. Elon Musk described the cabin space at the 2019 Starship unveiling at Boca Chica, Texas, saying that the pressurized volume would be around 1,000 cubic meters. He suggested that a future Mars transport version could theoretically carry around 100 people because 10 cubic meters per person offers significantly more room in zero gravity than it would on Earth, where you are stuck on one surface. To put that in perspective, the entire ISS, every module from every country assembled over 13 years, has roughly 1,005 cubic meters of total pressurized volume. A single Starship could theoretically match or exceed that amount of interior space in one launch. Now, NASA has taken formal notice of this potential. In June 2023, NASA selected SpaceX as one of 7 companies under the Collaborations for Commercial Space Capabilities initiative, known as CCSC2. This is an unfunded Space Act agreement, meaning no money changes hands, but it gives SpaceX direct access to NASA's space station expertise to explore how Starship might serve as a commercial orbital destination. This matters because NASA is actively spending billions to fund the International Space Station replacement through a separate program called the Commercial Low Earth Orbit Destinations Initiative. In July 2025, acting NASA Administrator Sean Duffy restructured the program, renaming Phase 2 to C3DO and allocating over $2 billion across 5 years, with the President's budget request including $272 million for fiscal year 2026. NASA wants at least 2, preferably 3 commercial stations operational before the ISS retires. This is where the competition gets fascinating, because SpaceX is not the only player in this race. In fact, they might not even be the most likely to build the first post-ISS station. The company closest to actually launching a private space station right now is Vast, a startup founded by cryptocurrency billionaire Jed McCaleb. Their Haven 1 station is a single module with 45 cubic meters of habitable volume, roughly the size of a tour bus, now targeting launch no earlier than first quarter 2027 on a Falcon 9 rocket, after slipping from its original 2026 date. Vast completed the final structural weld on Haven 1 in October 2025 and successfully flew a precursor Pathfinder mission called Haven Demo in November 2025. If successful, it would become the first privately operated crew-capable space station, small but real. Then there is Starlab, a joint venture between Voyager Technologies and Airbus, with partners including Northrop Grumman, Mitsubishi, and MDA Space. Starlab is designed as a single massive module, 8 meters in diameter, with 450 cubic meters of pressurized volume, about half the ISS in one piece. The reason it can be that wide is because it was specifically designed to launch on a SpaceX Starship. As of right now, Starship is the only operational rocket that can accommodate a payload that size. Blue Origin has announced a larger New Glenn variant with an 8.7-meter fairing, but that vehicle is still in development. Starlab completed its critical design review with NASA in February 2026 and is targeting launch around 2028 to 2029. Axiom Space is taking a different approach entirely. Rather than building a standalone station from scratch, Axiom is constructing modules that will first attach to the existing ISS, then detach and fly independently once the ISS retires. Their first module is targeting a 2027 launch. Axiom has already flown 3 private crew missions to the ISS, giving them more operational experience than any other commercial station provider. And then there is Orbital Reef, the joint project between Blue Origin and Sierra Space. Originally designed as a 10-person station with 830 cubic meters of volume, Orbital Reef has fallen significantly behind schedule. The two companies reportedly considered ending their partnership in late 2023 before reconfirming cooperation. It remains the most ambitious concept on paper, but the least certain to actually reach orbit. So, if all these companies are building stations already, why does the Starship station concept matter? Two reasons. First, even companies building their own stations need Starship. Starlab literally cannot launch without it. Vast plans call for Starship to carry their larger Haven to central node. The rocket's 9-meter diameter has become the defining constraint of next-generation station design. If you want to build something bigger than a submarine tunnel, Starship is currently the leading option. Second, the potential volume advantage is staggering. Starlab's 450 cubic meters is impressive. Orbital Reef's planned 830 cubic meters is ambitious. A single Starship configured as a station could theoretically offer over 1,000 cubic meters of interior space, though usable habitable volume after outfitting with life support and equipment would be less. Even with that reduction, the raw size advantage is a category difference. Independent engineers and space enthusiasts on the NASA spaceflight forums have proposed speculative interior layouts dividing a Starship cabin into roughly 7 decks, each about 2.2 meters in height, stacked vertically to provide multiple levels of habitable space. Designs might use offset openings between floors to prevent people from accidentally floating through multiple levels in microgravity. These concepts include crew quarters, research laboratories, exercise facilities, observation areas, and dedicated radiation storm shelters with water-lined walls to block solar particle events. But we need to be honest about what stands between this concept and reality, because the challenges are serious and none of them have been publicly solved. Radiation protection is a major concern. International Space Station astronauts receive 80 to 160 millisieverts of radiation during a 6-month stay. Stainless steel provides some shielding, but genuine long-duration protection would require water barriers, polyethylene panels, or highly experimental magnetic shielding concepts that remain unproven in space. Power generation is another gap. The International Space Station generates 75 to 90 kilowatts from 8 massive solar arrays spanning 73 meters. A Starship station would need similar or greater power capacity, and the vehicle is not designed with permanent station-class solar panels. Someone would need to bolt on an entirely separate power infrastructure. Life support is perhaps the biggest question mark. SpaceX has operated closed-loop environmental systems only on Crew Dragon, which is designed for short missions. The kind of systems needed to recycle air and water for months or years on a station are complex, heavy, and SpaceX has never publicly demonstrated them for Starship. And there is the basic physics problem of keeping the station in orbit. Atmospheric drag slowly pulls satellites down, requiring periodic reboosts. Starship has engines, but its methane and liquid oxygen propellants slowly boil off in space, meaning a long-duration station would likely require periodic refueling from tanker missions or an alternative reboost system. SpaceX has not yet demonstrated long-term cryogenic storage in orbit. Elon Musk himself has acknowledged these gaps, saying that SpaceX needs to fly hundreds of successful missions before putting people aboard, and that the design priority remains Mars, not low Earth orbit habitation. So where does all of this actually stand in 2026? Starship has now completed 11 integrated test flights. After a rough stretch in mid-2025 when multiple Block 2 vehicles failed during flight, SpaceX pulled off 2 consecutive clean missions with Flights 10 and 11, achieving payload deployment, Raptor engine relights in space, and precision ocean splashdowns. As of right now, Flight 12 is imminent, scheduled for mid-May 2026. It will debut the upgraded Block 3 vehicle with next-generation Raptor 3 engines, launching from Pad 2 at Starbase in Texas. SpaceX is also building Starship launch infrastructure at Cape Canaveral in Florida, and constructing massive new production facilities they call gigabays. The rocket is getting closer to operational status with every flight. And that matters because even if SpaceX never builds their own space station, Starship is already contracted to carry other people's stations to orbit. The vehicle is increasingly positioned to become a central piece of the post-ISS era, whether SpaceX builds a station or not. There is a nice historical parallel here. The Saturn V did not become Skylab. Its third stage did. Starship might follow the same path, not as the station itself, but as the vehicle wide enough to carry the next generation of stations to orbit in a single launch. Or, if SpaceX decides to go all in, a Starship could park itself in orbit and become something Skylab's designers could only dream about. A space station 3 times the size of America's first, launched in a single afternoon. Either way, the era of building space stations exclusively out of small modules may be coming to an end. And the rocket that was built to take humans to Mars is about to reshape what the sky above Earth looks like for the next 50 years. If you found this breakdown useful, hit subscribe. We cover the biggest developments in space and science every week.